Hello everyone, welcome you all. Today we discuss experiment number 9 on stability analysis for the system under different performance conditions. So the basic objective in this lab is to learn about stability of the system. So we used MATLAB to do it. What is stability? So the main idea about a system is stable if natural response approaches zero as time approaches infinity. Mild stable means that you have a sustained oscillation in the system. Unstable means that system natural response grows, so it means that system is unstable. So if we are giving some bounded input to the system and we get a bounded output, then system is stable. Now the other way of defining the stability is based on pole location. So if you have poles at left of plane S plane, and if we take the transfer function and look at the poles of the system, then system is stable. Mighty stable means that if you have a single pole at the origin or you have a pair of uh, imaginary poles, then you can say that system is marginally stable. Unstable means that if you have at least one pole at the right of plane, means that if the real part is positive, so your system will grow and system is unstable. Now let's look at the first task. Task 1 is find out the following systems are either stable, unstable with the help of step response and correlation. Now if system is stable, step response will have output that is not growing, okay, reaching to the step input. But if it is unstable, then it will be growing. So similarly, if we look at the pole location, it is at the left of man and so on. Now there are two systems given to us. G1 is 1 divided by S plus 1, G2 is 1 divided by S minus 2. So if we look at this system, this is a first order system, and in first case pole is at minus 1, second here is pole is at 2, so means that A is stable and B is unstable. Now we will see it using the MATLAB. So this is our task 1, and this is the table we have to fill it, that write your answer of task 1. Here you have to write the pole location, stable, unstable, and so on. Now let's open MATLAB here. So this is our MATLAB. Now in MATLAB, first of all, as I told you in previous video, so we have to start with close all, then clear all. So this will close all the figures, and clearer will clear the this workspace which is available here. Uh, then CLC will clear the command window. Now task 1, what I did, I start with an SN operator so that I can write the transfer function. Then I define G1 is 1 divided by S plus 1, similarly G2. Then I use the command pzmap here for G1, similarly pzmap for G2. Then what I did, I just printf that this is task 1, and I make the table that is required to us to do in the manual, that we have to write the system, pole location, stable, unstable, or marginally stable. Now if I just put a condition here, if pole is less than 1, then system is stable, else we will display this thing, else system is unstable. So similarly we do for second system with the pole P2. So this will complete our task 1 here. Okay. After that, what I did, I just used a figure command and plot the first system and second system. Okay. Now let me run this. If I run this task 1 here, so first of all I have to run this close or clear out. So when I do that, it will clear this command window and also clear the workspace. Okay. So after that, I have to come to task 1 here. So it took some time to do it. Now first of all, we have to define these two functions, that is G1 and G2. So let me Now after the command window is clear, just I run this first bit where I defined S and G1 and G2 here. Just I run here, evaluate. So look here, it will define G1 and G2 in the MATLAB. Okay, so if I write here G1, it will give me the result G1, similarly G2. So after that I have to find this pole location, so I just run this one. So that use pzmap commands to identify the pole location. So I have two poles, that is P1 and similarly P2. Because this is first order, so I have only two poles. Now want to run this one, this small command. So it what it did actually, it plot this thing. Okay. So it will plot that task one. We have system pole locations stable unstable. Now, if pole 1 is less than, then it will be stable, otherwise it will print that system is unstable. Now, if I run hold this command till the second one, also I plot the step response. So you can write these commands easily. If I do it, look here, this is task 1, we have systems G1, G2, these are the pole locations, and this tells us that system is stable or unstable. So this is the step response. We have here G2, G1. G1 is, if you look here, step response is sustained at the step input, but here it is going, so this is unstable system and this is stable system using step response. But similarly, if I use the other command, pole location, so here the pole location -1, 2, stable and unstable. How I write this bit that we have task 1, very easy. So first of all, I use command fprintf. Uh, /t means that you just want to give a tab space here. Then I write this and then task one. Then \n means that you want to write a new line. Now then I use a command display. What it display system, then pole location, then stable unstable. So it will look at the first line, print this task one, second one is system, pole location, stable unstable, as seen in command window. Now then I use a condition here, if pole P1 is less than 0, then I use a variable x and I use s printf. So this is used for string. So I make a string that I give the same uh, what you say tab, two tabs, then I write G1, then tabs, then I want to write the pole location. That's why, because pole location is real, so I put percentage %d for integer and \t again, two tabs, then I wrote stable, then I write the value which is stored in P1 using this pzmap. Similarly, I just write the display. If this is otherwise case means that if P1 is greater than 0, then it is unstable, so it will print this one. So similarly, I use this and x will print the string like this. So same thing I did for P2 code here. Okay, look at same command lines, and after that I just plot this table that is required in your manual. Then I use figure. I open a new figure, then I use subplot. So when I put 2 means that I want to plot two figures. 1 means that I want to plot at 1 location figure 1, that is step 1. Then I put x level. X level means that horizontal level. I put time seconds. Then in y level I put g1 of t, that is the time response of g1. Then sorry, step response of g1. Then I put grid on that will grid the plot. Similarly for subplot, again, I at the second plot I plot G2 with same time and so on. So when I run this, I will get this figure and this result in the command window. Now, if I move to next task, that is task 2, that says find out the following system are unstable, stable, marginally stable. Now here we have second order systems. So we have G3 divided by S square plus 2S plus 3 and so on. So again I have to find the pole location, stability and also the step response. So what I did for second, if I go to, I start task 2 here, then I write the name here G3 because first one for first task I call it G1, G2, here G3, G4. Then I wrote 3 divided by S square plus 3 static S plus 3. Similarly, 6 divided by S square minus 2 static S minus 3. Then find the pole locations here and zeros. Now I have to write this correctly. This is 3, but I didn't use 0. I use only poles for stability. Again, I print that this is task 2. Again, display system pole location stable, unstable. Then, because this is a second order system, so I have two poles. Then pole can be complex or real. So that's why I have to look at the real part of the pole. It can be real or complex. So in condition here, I put real of pole 1 is less than 0 and real of pole 2, then system is stable. This character is for characters 177 means that if I want to plot plus minus in the MATLAB, I can use this character 117. Now then I calculate the pole location, real one, then imaginary one, then I use this printf, again two spaces, then I wrote G3, then again space, then point 0.4 means that I want 4 decimal floating points number here to be printed, then string is for this x, that is plus minus 1 because you know that complex poles are in pairs, again point 0.4 for the complex one, then I put I here for iota. Okay, this I for iota. Then I put stable, then I roll this real part and imaginary part, that I use this using this command real and imaginary. Now if I move else, if this is not the case, this is unstable, then we have to again do same thing but for unstable system. Now if I move further for second system, I do the same thing again, but instead of if I, here I just have to write P4 because this is for G4. Again I find out the real part and imaginary part. Now when I complete this thing, then I use another figure, second figure I open it, and then I use subplot. Okay, subplot, I plot G3, G4 with time response G2. So if I clear this thing so that you will, if I run this task 2, what type of result I am getting here. This is task 2, just I can evaluate it. So it took some time because it's busy. There's some error here. I don't know why. Okay, I didn't copy all the tasks. I have to evaluate whole task. I do it again till this point. Just evaluate it. Okay, now I get the result. This is the step response for second order system. Again, G4 is unstable, this is G3 is stable. So it is variant from this pole location. Look here, G3 is a complex pole but with negative real part. So this is a stable system. And because this is a single at the right of plane, one pole is the right of, other is the left of, but the system is unstable. So this is your task 2. Now if I move to task 3, now here again we have the same question, but now it is third order system because it is 3 poles here. Now we have 3 systems here. Now here the denominator is same, only numerators are changed. Now again I have to fill this whole table here with A, B, C for 3 systems and find out that this is margin stable, unstable or stable system. Now if I go to my script here, now I start task 3 here. I just click double percentage sign. This will make us a separate section. So this is for task 3. So this means I am working in this in task 3 instead of task 2. Now again I define G5, G6, G7, that is 3, 6, 7, SQ plus 3, S square plus 2S. Now this is the pole location PC map G5, G6, G7. Now I print here is that I have to print the task 3 then pole location. So now after defining this transfer function busy map, then I print the task 3, then again display system pole location stable unstable. Now I find out because the pole has two parts, so I get the pole locations from here P1, P2, P3. The three poles, so I get three poles here. Then I just print it and identify that this is marginally stable, unstable. So I just put the conditions on it, and similarly for all the systems. And then I calculate again the step response. If I run this task, just evaluate this task. So look here, this is G5, G6, G7. These are the pole locations, and these are our marginally stable system because poles, one pole is at 0, 2 at the left of plane. So only difference is a bit different on the what you say step response. So you have to evaluate it further why step response is different overall. Here, because due to the numerator, we have different step responses. Now, if I go back to manual again, now this is task 3. Now, task 4 is based on this block diagram. So you have G of S, H of S given you here. C is the closed loop. Now, here we have to find first of all the closed loop transfer function. Then we have to find the value of k on paper that will make the system stable, marginally stable, and unstable. So here you basically have to use the routes criteria. So you just use the routes criteria, make the route stable, and identify the values of k for stability. So when I did it, and I find the range for stability between 0 and 16. So at 16 is marginally stable, and if it is greater than 16 is unstable. Now part A says that draw the step response of the system for gain of k minus 1. Means that where k is the value calculated marginally stable response. So in my case k was 16, so the k minus 1 is actually 15. Now I will draw the step response for this part A, then again draw the step response when k is marginally stable, that is k is 16. Now then write in the box. So what I have to write in the box is the stable, what is the value, marginally stable, what is the value. Now I move to my script again. Now this is task 4. Now here again start with task 4. I define G is 1 value because I calculate k 16, so I put k equal to 16. That is the value of margin stable. Then I calculate system 1, that is k minus 1, and static G1 to take the feedback of the system. Again system 2. Then I print task 4, and again I put cases and values of k. Now f print I use, and static D will print the value of k minus 1 as an integer. Again f print margin stable, I put the value of k. Now I then again use the figure and subplotting. Here I need only two plots, so I put 2 1 1, 2 1 2, and system 1 system 2, and then margin stable and unstable. So in last task we have to, when I need three subplots, so I have to put 3 here. Then I start 1 1 1 2 1 3. It will plot in horizontal direction. So now for this task, if I run it, task 4, till this point, just evaluate it like this. So this is the task case, stable, unstable. So these are the values 15, 16. So look here, step response. This is for stable because it will converge after around 170. But for margin stable, it is sustained oscillations. So this was your task number 4. Now, if I move to task 5, so task 5 is basically from your lab number 6, and it is written task 3, but it was task 4 in lab 6, that is about the DC motor, and it is actually a first order system. So, what I did here, I just consider the first order system. Now, for this block diagram, the main idea is you have to use the DC motor cross function, that is actually a first order with omega, but you have to introduce an integral for angular uh, directions. So angle of the instead of speed, you have to use the angle. So that's why you have to introduce with integral for the first orders. Now here the main task is to use the PID controller. So this is a control and normally we use which has three gains. One is known as P for proportional and I for integral, D for derivative gain. So when we combine proportional integral derivative, so it becomes a PID gain. So we have to use this whole block diagram and look at the behavior of different gains. So we have to write the proportional block effect, integral block effect, and then we have to write about the derivative block. So what I do for this task implementation. So I before this I have you have to look at the PID. So PID is available in the MATLAB as a function of KP for proportional gain, KI for integral gain, KD for derivative gain. So this is the transfer function, that is KP plus KI divided by S plus KD multiplied by S. So this is the transformation you will get for PID. Now what I did here in task 5, first of all I defined this transfer function, that is theta divided by EA, that is KT divided by S into S plus alpha. Now here I put alpha equal to 1 and KT equal to 1, so G becomes KT divided by S direct S plus alpha. So for proportional gain Kp, so I introduce a figure and then I use I equal to 1. Then I use the loop of Kp, that is from 1 to 8 with 2 increment here. So I use system of I. I means that first system where Kp equal to 1, and I2 means that when Kp equal to 3 and so on. So I use the feedback Kpg is available time 1. So then I also want to know the which K I use for system 1. So that's why I just note the Kp value and store in KKI. Then I use step response and will plot the step. Then I increment the I so that next time I will save the next value in KK system. So then I hold on because I want to plot in a single figure, and then I end the process. So this is the first one. Then after that, I give the legend so that I know that which K give the which response, which type of response. So I use legend. So legend, I introduce a command inside as string printf AP equal to percentage D, that gives the values of AP that I use here. It is the first one, then is the second one, then is the third one, then here is the fourth one. So this will command here plot the legend. Okay. After that, I will introduce the title of the figure, that is step response variation using proportional gain KP. Then I put the grade. Now I just run this first part of task 5. Let's see what we get here. So this is task 5. Now what we get here, we get a figure here, very nice figure here, time in seconds, amplitude, we have this different responses. So this responses is with different variation of K value. So if you look here, so as you increase the K value, your overshoot is decreasing and your steady state error, your system is settled quickly. Okay, so the main idea is that you increase the value of K, so your overshoot is increasing, but your response is a bit fast. Okay? But as you decrease the value of K, your rise time more. Okay, this is the for k equal to 1. So this is the analysis. So what we get from here, when you increase the value of k, so you have more overshoot but less steady state time. Okay, it also reduces the steady state error. So this is what we get when we do with proportional gain only. Now in task second, where we have to introduce the differential gain. So what I did here, I use the no for second one integral. So remember this thing, integral gain is only used when your system is a bit stable and it has only what you say constant error. Then you introduce an integral, it will increase the type of the system and remove the constant error from the system. But when system is oscillatory or system has much oscillation, if you introduce the AI, it will introduce further oscillation and system may become unstable. So only KI is used when you are required to remove the constant error from the system. So what I did again for integral KI, I introduce again KI, and now variation is from point 0.1 with the increment of point 0.2 and 1. Then I use this command is PID that I show you, which is available in MATLAB. Now I fix the KP value, the last one, that is I think is 8, and with KI, that is very with this will give me C, that is the controller. Now I use the feedback again, C static G comma 1 for system 1. Again I just save the value of KI so that I know what happened when I vary the K. Again I introduce a step response, then increment, hold on. Then after that I introduce the legends here because they have 5 values, so I put KI 1, 2, 3, 4, 5. Then step response variation using integral KI and then grid on. Now I just run this one. Okay, yeah. So now I get, so this is the response I get. I told you that what KI actually do is removing the steady state error. Here steady state error is already removed, so there's not much effect you are seeing here. So what you may see is that you have variation in the response in terms of oscillations. As you increase the K, it will give more oscillation. So remember that KI value, that is the gain, integral gain, only works for a steady state error. Now I move the last bit, that is D term or differential one, that is KD. Now again I vary the KD from 1 to 2. Again I use the PID command for KP, KI, KD and feedback. So I have the same what you say coding here. When I run this one, again step response for KD variations. So when I do that, so this is the result. So this give us very good analysis here. Now if I increase the KD values, you look here KD1, so you have this response, that is blue one. Right, KD 7, so you have this response which has no overshoot. So this means that whenever you use the differential controller, it will remove the extra energy from the system. Or in other words, it will remove the oscillations from your response. So it will remove the energy, so system is more stable. So it will make the system much stable because differential introduce a zero in the system. So that will work towards the stability of the system. Uh, so this is where you can introduce derivative when you want to remove the energy of the system. So this is the one way. Now this is the whole script I wrote. Here we have to look here. I just calculate here. In this case, we have only 4 responses, so I put KD slash percentage D means that you want to print here the integer K1, K2, K3, and K4. Okay. So if I run the whole script here for this lab and see how this lab performs, so look here. After running, this is the task 1, then task 2, then task 3, then task 4, and then at the end we have task 5. So with we have all the figures. This is the last task figures, the second, this is third, fourth. So this is one way of doing all this. For last task, he also want us to do some further analysis. So for that case, I made a simulated diagram also. We have a step input, then we have a summer here. This is the controller I make. If I double click on it, how I did, I make input. This is KP gain, this is KD gain, this is KID. So for KD, I take the differential. For KI, I take the integral. Then I sum up. Then I output. So this make a PID controller. And this is the transfer function, and this is the integral to get the angular. This is the velocity. Then I take the feedback and do it. Now, PID block is also available in the simulation. So I just drag the PID block. So you can find this block if you look here. So we have this here. It is available here. This is the PID block I just put here. Now, if I double click on PID block, so this PID block has this is written as a PID block. This is a continuous time. It can be a discrete. So we have a proportional gain, that is I give here 8, then integral 1, then derivative 7. Then there is a filter coefficient. So what actually did here in this PID, you have a proportional gain, you have integral gain, that is I divided by 1 by s plus d, and divided by 1 plus n divided by 1 by s. So this is differential. Actually what happened, I told you that whenever we introduce a differential, so S means that in frequency domain it is if there is no real part, then S can be directly proportional to j omega. Omega is the frequency. So when you increase the frequency, it will affect. So this means that because noise is at higher frequency, so your differential will affect the derivative term. So that's why we use a low pass filter with the differential, so that it is not following the noise. Your controller will not follow the noise, but it will compensate the error. So that's why. So this is, if I say okay, so these are two implementation. If I run it, so it will compile and run. So you see here, we have a result here. This is with our controller the same game, but with the filter control we have a different result because of the filter. Okay. Now there's another important point we have to note, that this will give us another help here. In this block we have a button available, that is tuning. That is actually a facility available us to tuning means that to find the best values for proportional, integral and derivative for this system. So if I click on this, it will run an optimization scheme. First it will rewrite the system, then run an optimization scheme to find out the best values for proportional gain, integral gain and derivative gain. So here we can give the specification also. So what we are doing here is that here we look here, this is the tuned response and this is the block response. So if I want to use that one, I just have to click here, update the block. Okay. So it will update the block, and just I cross this. Look here, this is the tuning values that is calculated using the optimization. When I put OK, it will use this value. So now I have separate different response this time. So this is the way you can use this block for tuning. So this is all about our lab 9. So thank you.